0.00 kilogram particle moves along the x-axis. Its position varies with time according to x equals t plus 2.0 times t to the t times t cubed, where x is in meters and t is in seconds. Find A, the kinetic energy at any time t, B, the acceleration of the particle and the force acting on it at time t, C, the power being delivered to the particle at time t, and D, the work done on the particle in the time interval t equals 0 to t equals 0.
So we know the mass of the object. We know the position function as a function of time along the x-axis. We're asking for the kinetic energy, the acceleration, the net force, the power, all as a function of time, and then the net work done on the object from 0 to 2 seconds. Travis, please begin.
Well, the derivative of displacement as a function of time is the velocity as a function of time.
So the velocity is going to be equal to the derivative of position as a function of time. Keep going.
And kinetic energy is equal to 1/2 velocity mv squared.
I agree with that. Let's do this first, then we'll get there.
Oh, okay. All right.
Yeah, that's fine. I'll write that next. I just
So
wanted
that's equal to 1 plus 6t squared.
1 plus 6t squared. This is the velocity as a function of time. That's going to be in meters per second. And as you said, the kinetic energy is equal to 1/2 mv squared. So the kinetic energy as a function of time, kinetic energy as a function of time is going to be equal to 1/2 times the mass, which was 4, times the velocity, which is 1 plus 6t squared, that quantity squared. So this is going to be equal to 2 times, is this foiling or unfoiling? I can remember. This is foiling? Okay. So 1 times 1 plus 12t squared plus 36t to the 4th power. So kinetic energy as a function of time is going to be equal to 2.00 plus 24.0t squared plus 72.0t to the 4th power in, of course, joules. Part A just asks for the kinetic energy as a function of time. There it is. Part B, we need the acceleration and the net force. Gary.
Can you read that?
Yes, we're looking for the acceleration and the net force for part B here.
We can use the derivative of the velocity one.
Okay. The derivative of velocity as a function of time is equal to what?
12t.
Not quite what I was getting at, but that's fine. So we have 1 plus 6t squared, which is equal to 12t, but that's equal to what? On the far left. The acceleration. Okay. So the acceleration as a function of time is equal to 12.0t, and that's in meters per second squared. That's part of part B. Mohit, we're also looking for the force on this object, the net force.
Well, you can just multiply by the mass.
Because that is Newton's Planck law.
Second.
Good. So we have sum of the forces equals mass times acceleration, where the force and the acceleration are both vectors. That's going to be equal to the mass, which is 4, which is 4 times our acceleration, which is 12.0t. So the net force as a function of time is equal to 48.0t newtons. Part C, what is the power delivered to this object as a function of time, the net power? De Silva.
It is not exactly sure. I think it's an integral. Not 100% sure. No, it's the force times velocity.
Catherine, is it the force times the velocity?
Dot product.
Thank you, Catherine. It is the dot product of the force and velocity. That is up there with the things that you will forget. Please do not. So the force we have, the force is 48.0t. The velocity we have, it is 1 plus 6t squared cosine of what angle, and how do we know? Look.
It's the angle between the force and velocity.
Which is what in this particular case?
0.
0. You know this because?
Force moves it in the direction it moves it.
That would be the force and the acceleration. We know that's true for the force and the acceleration, but the force, net force, isn't necessarily in the direction the object is moving. It could be decelerating the object, for example. So they aren't necessarily in the same direction. Gary?
Because they're both positive, I'm assuming that's going to be.
Therefore, because the force is positive and the velocity is positive, they're both going to be in the same direction. Therefore, the cosine is going to be cosine of 0. So what we end up with is 48t plus, oh boy,
288.
thank you. 48.0t plus 488. 288, good, yeah, that makes sense. 288t cubed, all in watts. Part D. What is the work, net work delivered to this object from 0 to 2.0 seconds? Michael.
So just the integral from 2 to 0 of 48.
Of what?
48. Right, because the force is 0. Is that it?
Okay, all right.
Okay.
Wait, let's start with the equation. What's the equation? The equation for work.
Is
The integral.
x5 on the top. Yeah.
From the initial to the final.
Yeah. And then the force x, then dx.
Okay, so the integral from the position initial to the position final of our force, which is 48t with respect to position.
Isn't the integral of power?
Work is equal to the integral of from initial to the final position of force with respect to position. This statement is true. This we can't do. We're looking at taking the integral of something that is with respect to time with respect to position. Unless you want to do U substitution, which most of you don't know what it is, I wouldn't suggest doing that. You could, but there is an easier way. Pontarella was close. I want to know what he was getting at. Go ahead.
Do you use the network equals the change in kinetic energy?
The network equals the change. We probably could go through and do it that way. We certainly could go through and do it that way. We'll get the same thing. That's not the way I'm going to do it this time, but yes, we could actually, because the kinetic energy is, we have the equation for it. We could do final minus initial of that and use 2 seconds. We'll get the same thing. I want to do it a slightly different way just to show something, because it's something that we often neglect and forget. Although that is another one we neglect and forget. So just to make sure people understand, the issue is we have time. This is from 0 to 2 seconds, right? So this is not as a function of position. That's the issue here. Okay. Winter.
Take the integral and then do a function of time.
You mean just change it to t? Right. You can't just change it to t. It doesn't work that way. It would be nice, but no. Power equals.
Oh, wait.
So the
Work as a function.
The derivative of work as a function of time. What can we do with any derivative equation? We can rearrange it and make it into an integral. So we have dw equals power times dt. We can take the integral of both sides. We get the change in work equals the integral of power with respect to time from the initial to the final time. So again, remember, anytime you have an integral, you have a derivative. Anytime you have a derivative, you have an integral, because they are related to one another. So we can do the change in work is equal to the integral from 0 to 2 seconds of the power, which is 48t plus 288t cubed with respect to time. Mohit, I do want to point out, you are absolutely correct, we could have used that, but this gets to review this piece, which is more important in my eyes. So, please take the integral of this equation. Sarah Jane.
48t squared over 2 plus 288t to the 4th over 4. The brackets from 0 to 2.
Great. So let's bring it up here for space. So the net work, the change of work from 0 to 2 seconds is going to be 24, I'll just do it 2 steps, 2t squared plus 288 divided by 4, please. 72. Yeah. T to the 4th power from 0 to 2 seconds. So 24 times 2 squared plus 72 times 2 to the 4th power minus a giant 0.
1248.
1248? 1248, what, De Silva?
Joules.
Joules. So with sig figs, we'll go with, what was it, 2? I don't know. We'll go with 2. 3 looks more fun. 1250